There we go. All right. So today we're going to be covering Unit 3, Lesson 2, right? Conditional probability. So I have my notes open right now, so let's go ahead and get into it so you guys can copy this down and get going here. So conditional probability, like I said, right, is basically a condition that occurs, right? You make your screen wide. This is as wide, I think, as it's going to get, guys. Sorry. I don't know how, I don't think I can I can change any more of that. Is it okay? Can you see that okay? Or is it like not viewable for you? Hoping it's okay. But yeah, conditional probability is the probability that an event of an event given that another event occurs, right? It's a condition. I pin it to my screen. Ah, okay, that works. Hopefully that works. So, right, it is the probability of an event occurring given that another event occurring. That's the condition, right? The condition is this happened, so this has to happen, right? Next thing after that is going to be seeing the difference between independent and dependent events. And then last but not least, which is kind of related but not really, is calculating the probability of two events or more occurring in sequence, one after the other, right? And how does conditional probabilities affect those values? So anyways, let's take a look here. Conditional probability, right, is given by this definition right here. It's the probability of an event occurring given that another event has already occurred. And we write it using this notation right here. Probability of B given A. Probability of B given A. That's basically saying, what's the probability of B occurring given A has already occurred, right? What's the probability of B occurring given that A has already occurred, right? So let's take a look at this example right here. Let's say we were drawing two cards in sequence from a standard deck, meaning I draw one card and then I pause and I draw a second card. Hold on. I should have had this ready. Where are my deck of cards? I have a deck of cards. Are you over here? No. Are you a deck of cards? No, you're not it either. No, you're. No, that's not it. Are you it? No, you're not it. No, you're a pen. Shoot. I mean, I don't really need the deck of cards, but I feel like it would make my point a little bit better. Give me 1 second, guys. Well, I'm a little set. I don't know where I put my deck of cards. Ah, there you go. Ah! All right, sorry about that. Had to go find my deck of cards. This is my lucky deck of cards. I've had this deck of cards since 2007. Had this deck of cards for like 13 years. Yeah, it's like almost falling apart, but not quite. All right, so here's the idea, right? Earlier in our warm-up today, right? Egyptian War. I wouldn't play Egyptian War with this one because I don't want to ruin it. The card's already kind of bent, but old. So here's the idea. Earlier, I asked you guys if you were to draw a random card from a deck, right? What's the chances that the card you draw is going to be a king, right? And you guys told me there's 4 kings in a deck, so it'd be 4 out of the total of 52. Now, our problem right here is a little bit different. This one's asking, there are 2 cards being selected in sequence. So you're going to draw 1 card, right? And then you're going to draw a second card. Now, they're asking for the probability just of the second card, not of the first card. They're just asking for the second card. They're asking, what's the probability that the second card is a queen given that the first card is a king? So the probability here will be written like this, right? What's the probability that the card that you're drawing is a queen given that the first card that was drawn is a king? Now, in our warm-up today, we saw that the probability of you drawing a queen was 4 out of 52. The probability is going to change in this problem. You know why? It's no longer, well, it's still going to be 4, by the way. How many queens are in the deck? There's 4 queens. But here's the part that's trippy. It's not going to be out of 52. Why is it not going to be out of 52? Anyone have any ideas? It's going to change. And here's why. So what has happened? What is the condition that has occurred in this problem? You drew a card and you got a king. Now they're asking, what's the probability? Your second card that you draw from this deck is going to be a queen. Now there's 4 queens still left in the deck. But the first card that you drew out was a king, and I'm holding it off to the side right here. Dang it, that doesn't stay anymore. My forehead not oily enough. There you go. So you drew your first card out. It was a king. How many cards are left in the deck?
51.
51, that's right. So the probability of you drawing a queen as your second card is no longer 4 out of 52. It's now 4 out of 51. Why? Because this king is stuck to my head. So there's only 51 cards left to draw. So that condition has been changed now, right? I'm sorry, the probability has been changed because of this initial condition. You drew out this king, there's only 51 cards left. Now you have a chance of a queen that's coming out to be out of 51 instead of the total 52. So that's how conditional probability works. It's you take into account, am I putting that king back? If I put the king back, then yeah, it's out of 52 still. But if I don't put the king back, then it's now out of 51, right? Does that make sense? It was my favorite game to play with students is having you guys try to guess the next card, right? And I would not put the card back. And I would ask students, if that's the case, if I'm asking you to guess the next card, but once you guess and if you guess wrong, the next person gets the guess, but I don't put this card back. So the king of clubs is now out, and I ask the next kid, right? You understand then, the later you go, the more likely you're going to get it right because all the cards that I keep taking out, I don't put back. The odds get better and better as I keep taking the cards out. So at the beginning, the first kid has a 1 out of 52 chance of getting it right. And if we go through the whole class of 30 students, the very last student will have a 1 out of 20 chance of getting it right, right? So those probabilities can change if you don't replace those cards back in there. But yeah, that's it. How do I know that that's 4 out of 51? It's because that king was taken out and it changed the probability. It changed the number of cards that were in there, right? Isn't that kind of neat? I think it's kind of neat. So that's that one right there, guys. Hopefully you guys got that down. That's conditional probability in a nutshell, right? That's literally all it is. It's just calculating that. Let's go ahead and take a look at this one. You guys probably learned conditional probability in your other math classes using these charts. Does this chart look familiar? Have you seen this before? Where it has like one event occurring and then it has another event occurring and it kind of overlaps them like this. So like in this case right here, no, you haven't seen it? That's all right. So I'll show it to you this time. So what this states is there's 52 children with high IQs, and then there's 50 children with normal IQs. So they're looking at a total of 102 children. Out of the 52 children that have a high IQ, 33 of them have this gene present that apparently, let's read this one. The table shows the results of a study in which researchers examined the child's IQ and the presence of a specific gene in the child. Find the probability that the child has a high IQ given that the gene is present in the child. I completely read that sentence wrong. Given that the child has the gene. That's weird. The word present was up here, but I read that. Anyways, I'm sorry, I get easily sidetracked. But yeah, what was I talking about? So when you look at this chart, Louis, you're looking at a breakup of those data values, right? So we know that 52 children have the high IQ and 50 children have a normal IQ. We also know that 72 children have the gene present and 30 children do not have that gene present. We don't know what that gene is. They're just saying it's this specific gene that they're talking about in here. And we're going to figure out what the heck that is. So how do you calculate given probabilities for something like this? Let's take a look here. So how would I write this out? I would write this out as the probability, right? What are we focusing on? We're focused on the probability that a child has a high IQ. So that's the main focus right there. What's the probability that they have a high IQ? Given is the part that comes afterwards, after that line. So given that they have the gene. Given that they have the gene. Well, here's the thing. If I was just asking you, what's the probability that they have a high IQ? The probability that they have a high IQ, I think a lot of you guys want to say it's 52. Would you guys agree? Out of what, though? You probably want to say 52 out of 102. And if you're just asked to give me the probability that you pick a kid that has a high IQ, that's right. Calvin, high Q. You know, I still don't understand why it's called high Q. The main character isn't named high Q. Or anyone on the team. And it's about volleyball. Or is high Q what they call volleyball? And I should look this. Anyways, why are you distracting me, Calvin? Easily distracted, knock me. All right, so here's the thing. It's not equal to 52 out of 102, right? That's only the probability of a high IQ, right? It means volleyball. Does it really mean volleyball? Does IQ really mean volleyball? The anime is literally just called volleyball anime in Japanese. Now, Giselle's on the right track, and Isaiah is going with that idea as well. What would you call it? We'll talk about it later, Calvin. It distracted me because Isaiah and Giselle are trying their best to keep me on track here. And you guys got the right idea. You start looking at the other numbers that are involved, right? Giselle's looking at this 72 down here. Isaiah's looking at the 52 still, but he's also looking at the number 33. And here's what you need to focus on. You ready? The given part, that the child has the gene, means that you only focus on the kids that have the gene. Given that they have the gene means that these are the only kids we care about. I know that sounds messed up because, you know, there's kids without the gene, but for the sake of calculating this probability, we're only focusing on the kids that have the gene. How many kids have the gene? How many kids have the gene in total? It's not 33, it's not 39, it's actually 72. So this is going to be out of 72 because the sample space is every single kid that has the gene. And Giselle's got the second part already. Out of those 72 kids that have the gene, how many of them have a high IQ? I can't not hear it now. IQ. Have a high IQ. Out of the 72 that are there, 33 of them have a high IQ. So what's the probability that you select someone with a high IQ? I take responsibility. Oh, Calvin. It's 33 out of 72. And that's your answer. And that's your answer. Does that make sense? Are you able to see it? Are you able to take a guess at that? The idea is, what are you looking that's given? When they tell you it's given, that means that you're focused only on that specific topic. Once you focus only on that specific topic, you focus then on what the original probability was, which in this case was high IQ, and write that number down on top of the total of what you only care about. I know it sounds weird, but we'll try another one. Let's try another one, okay? Here, let's go into this case right here. So I'll leave this example right there. See if you can follow my example to do the you try. Try the you try on your own notes. See what you get. And give me your answer on the Pear Deck that we are working on right now. So I'm going to move your Pear Deck to a blank screen. On the blank screen right there, can you give me your answer for number 1 and for number 2 on the Pear Deck once you've worked this out? So try what I have on screen right now. So you look at the will do, and then try to find the answer for the you try. So go ahead and do that real quick. I'm going to go ahead and set a, what's a good amount of time for these two problems here? Let's go with a 3-minute timer. 3-minute timer. 3-minute timer sounds good. We'll let that start counting down right now. So try these out. Try these out. Don't just wait for me to do it. Try it, and if you feel like you don't know what to do, try it and get it wrong. Right? Best way to learn. Best way to learn. I will not put you on blast if you get it wrong. That only goes to Lewis, no one else. Right? Everyone else, don't worry about it. If you get it wrong, I'm not going to put you on blast for it. All right? So just try your best. I don't know if you actually heard me or not, Miguel, but we'll see. But yeah, let you figure that out. While you guys are working on that, this deck of cards, right? I've had since, like I said, 2000. I want to say 2007. It was around the time I learned how to count cards, so that's why I kept this deck. It was like sentimental values. But yeah, if you guys ever want to learn how to count cards, let me know. I can teach you guys. Which decks come with a better box or case? Some decks do. If you look at if you look online, it's just not a bicycle deck. There are special decks out there that you could buy that have like special carrying cases for them, but they're gonna cost a little bit more. But yeah, the paper ones suck. Yeah, I agree. This one, I'm surprised this one has held together as long as it has. The flaps on the sides here are completely gone, but the top flap is still there. You know. So I appreciate that right there. Cards themselves are okay. I had one student who actually was a card like he liked doing things with cards, and I thought that was pretty cool. He would like shuffle them differently and whatnot, but the deck he had like special designs on them. I was like, ah, that's cool, neat. All right. We got about a minute left. Let me take a look at some answers here, and then we can go over them together. Let's see here. What we got? We got about 10 answers out of 32 of you, and that's okay. Let me take a look here. I want to take a look at some of your answers here. And even if you got it wrong, I'm going to give you guys some points for attempting this. So we're doing the you try right here. And I'm looking at the 10 responses that I have so far, and I'm going to give you guys. Oh, that ends up putting you on blast. That's fine. I'm giving you points. I'm going to put you on blast. Even. Anyway, let's just do that. Lights, can you please stop freaking me out by turning off like that? All right, so we're going to go ahead and give some points here to the people I see. I don't know if they're right or wrong, but at least you attempted it. So. Here we go. I'm going in order here. Well, not in order. I'm going in order of when I received an answer from you. All right. I don't know if they're right. Just giving you that heads up right now. So I see your attempts. I think they look right because a lot of you guys are sharing the same answer. It looks like. Yeah, it looks good. Where are you? There you are. There you are over here, and then right there. That emoji though is Jasmine. Have some more faith in your answer. Kevin, I got you as well. Michael, I see you in there as well. Lewis, tell me, do you think you deserve points for that? What did I do? Nothing, Lewis. Right, you're right. Nothing. You did nothing. I'm confused, sir. Oh, I was just looking at your drawing, Lewis. All right. Well, we'll do it. We'll do this together, Lewis, so you can have it in your notes. All right, we got you, Jared. Sky. Where are you, Sky? There you are, Sky. Ooh. Adriana is typing in complete sentences for me. I appreciate that. There we go. There you are. Adriana, Christina, I got you as well. Where are you, Christina? There you are. Okay. Looks like you guys here. I'm going to go ahead and go with 3 points under commitment. You guys are actually doing the work with me here. I appreciate it. So let's take a look here. So Lewis, we're over here right now. We're doing the notes, and we're under the you try. We just did the will do, right, for the given part, and this was the answer we got for that one, Lewis. So let's break this down piece by piece, and let me know if you're still confused once we break this down piece by piece. Okay, so let's focus here. Let's look at number 1. Find the probability that the child does not have the gene. Does not have the gene. How many children do not have the gene in total? Right? That's what we need to look at. How many children do not have the gene? And if you look here, what's the probability that they do not have the gene? Right? Probability that do not have the gene. How many children are here that do not have the gene? Look at the chart. Look at the chart. This is the chart that we use to find that out, right? And I'm hoping you guys can see it. There are 30 children. No, we're not focusing on high IQs, right? We're not focusing on high IQs. We're only focusing on no genes, right? The gene is not present. So we don't actually care about the 52, right? We don't actually care about the 52. We actually don't care about the 19. Well, we care about part of the 19. We care about all of the 19. So how many kids don't have the gene? 30 of them. That's 30 that we care about. Out of what? How many kids total? How many kids total? How many kids are we looking at? How many children are we looking at? 102. That's exactly it. That's right. Oh, I see it. You guys all typed it out. That's beautiful. That is right. That's your answer. Why is it out of the total 102? Because they're not giving me a condition. We're not focusing on one type of kid. We're focusing on all the kids. And out of all the kids, 102 of them, 30 of them don't have the gene. 30 of them don't have the gene. And that's it for part 1. That's your answer. Now, part 2 is a little bit different. Part 2 is telling me, find the probability that the child does not have the gene given they have a normal IQ. So there's more to this one, right? For number 2, I'm looking for the probability that they don't have the gene given, you see that vertical line? That's my given that they have a normal IQ. Normal IQ. So this one changes a little bit. Whenever you see the word given, I need you to realize you're no longer looking at the total. You're no longer looking at the total of 102. Given restricts your probability to what it is that you need to focus on. And in this case, I need to focus on children that have a normal IQ. How many children are there that have a normal IQ? Where is that? What do I focus on? I focus on this normal IQ right here, all the way across. You see that? And Lewis and Carwin combined gives us those numbers. Carwin's saying the total number of kids that have a normal IQ is 50. You are correct, Carwin. There are only 50 kids we care about. And out of those 50, which one do not have the gene? Lewis is saying, never mind. Sky's going with 11. What are you saying, never mind to? Oh, no, Lewis, that's fine. You're just pointing it out. There are 2 numbers there that we need to focus on out of that chart. And Sky, you are right? 39 has the gene present. 11 have the gene not present. And I'm looking for the not in this case. So it's 11 out of 50. And that's it. That's how you calculate probability when there's a given condition. It's the same type of idea of calculating probability before, but now you have to pay attention to what is restricting your probability. Does that make sense? You focus more on the fact that, like, oh, there's 102 kids here, but given that the fact I'm only looking at kids with a normal IQ, I only want to look at 50 of them, right? And out of those 50, how many of them don't have the gene? And it looks like out of those 50, 11 of them don't have the gene. Can you explain the thing with the parentheses? Sure. The naming part of it, Lizzie, is it this part right here? This part unboxing? Yeah? Oh, okay, okay. So the thing with parentheses is it's just notation. So P stands for probability, and what's inside the parentheses is what the probability of what it is that you're focusing on. So for number one, what's the probability that the child does not have the gene? I just wrote it as not gene because I'm lazy, but technically you're supposed to write it as P of child does not have gene, right? So I'm just being lazy. But part two, right? Why do I have this vertical line right here? This vertical line represents the word given. It's like a shortcut, so you don't have to write out the word given. So whenever you see the phrase given, this is the notation for it. It's this vertical line. And the way we read this is the probability that the child does not have the gene given they have a normal IQ. So that's how the things in the parentheses came to be, right? And usually the part that's in the given part of it, that's what I usually highlight on the chart. Does that make sense? Like, given that the child has a normal IQ, I looked at the normal IQ and I looked at all the values for that one only. I did not care about the high IQ at all, knowing that I only care about the normal IQ. That's how that works. Does that answer your question, Lizzie, about the parentheses? It's just notation. Got it? Thank you. Awesome. Awesome. Sweet, sweet, sweet. So that's how that works. That's how conditional probability works. Kind of neat, right? Kind of neat. So that's that one right there. Let's take a look at this one right here together. It says you try, but I want to talk about this one together here. Let's take a look here. This is a real life application of doing conditional probability, by the way. BRCA gene in the general population, one woman in 8 will develop breast cancer in the general population. Research has shown that approximately 1 woman in 600 carries a mutation of the BRCA gene, which is really scary. About 8 of 10 women with this mutation develop breast cancer. This was calculated by Susan G. Komen, Breast Cancer Foundation. Scary thought to look at, because normally, this is already a scary value right here. This is like terrifying to me. In the general population, just in regular, everyday population, 1 woman in 8 will develop breast cancer. Okay, so the probability, right, to develop breast cancer. This is a sad thing to talk about, but it is a statistic that is out there. Right? The probability of actually developing this without knowing anything else is going to be 1 out of 8. Now, research has shown that 1 woman in 600 carries the mutation of this BRCA gene. So what this is asking now, what's the probability of you develop, oh my God, my handwriting is terrible. Let's try it again. Develop breast cancer given that they have the BRCA gene. Now you look at this and you probably want to do some calculations with this 1 out of 600, but that actually does not need to be done, right? They're just telling you that generally that 1 out of 600 women have this gene. But if you do have this gene, what's the probability of you developing breast cancer now? It's no longer 1 out of 8. It's now changed to 8 out of 10. And that's it. That's your answer for this one. The answer for this one is 8 out of 10. Where did I get the 8 out of 10 from? It's right here. They tell you about 8 out of 10 women with the mutation will develop breast cancer. So the probability of you developing breast cancer, given that you have the mutation, is 8 out of 10. Scary number. But that's it. That's how conditional probability works, right? That's all you're really looking at is what are the conditions that we're focusing on, and how does that affect the probability of you getting something. So if you don't even look at if they have the gene or not, the chances of you developing breast cancer is 1 out of 8. But if you have the gene, given that you know that you have the gene, your probability jumps up to 8 out of 10. So a lot of women who end up having this gene will go and get a, I think it's called a mastectomy. Is it a mastectomy? I should know this term. But they'll go and have the surgery before they even get diagnosed with breast cancer because it's just that much of a danger, right? It is so high. What is that? It's when they remove your chest. They remove the fat tissues underneath there just so that it can prevent breast cancer developing. If they know that you have this gene, the probability ends up being so high that you'll get it. People will do it as a precautionary thing. So that's one of the things that you can do when you know. Sounds painful. Yeah, it is. But cancer is more painful. Like Angelina Jolie. Yeah, actually. Yeah, she did a double mastectomy. Yeah, she got both removed as a precautionary thing, I think. I don't think she actually was diagnosed with breast cancer, but she did it as a precautionary thing, I believe. I could be wrong. I don't actually know her life, so, that's that. So that's that you try right there. I didn't mean to be such a downer about it, but it is an important statistic and it is an important probability that you should know about. All right, let's take a look here. Independent and dependent events. Independent and dependent events. Independent events occur. The occurrence of one of the events does not affect the probability of the occurrence of the other event. Meaning, if I looked at the probability of B given A is just equal to B, or the probability of A given B is just equal to the probability of A, that means that the events are, wait, what? That's not right. Oh yeah, no, these are independent events. These are independent events. Right here. I don't like this sentence being right after it. If events that are not independent are considered dependent on each other, meaning that this value is going to be dependent on what occurred earlier. So things that are not independent are considered dependent. I don't like that location of that sentence. It shouldn't be in there at the same line as that one. That looks weird. But yeah, so what does this mean? You probably have heard this before, right? If you flip a coin and it comes up heads, it doesn't tell you what the next coin flip is going to be. You flip the coin once, it comes up heads, and then you're going to go flip it again. Hey, it came up heads the first time. Does it affect the probability of the second coin flip? And I'm hoping you're saying no, right? If you flip a coin, you get heads, and you go to flip it again, the coin isn't going to be like, you know what, I landed heads earlier, and I think I'm going to change it up just to make it different, right? That sounds ridiculous, and it is ridiculous. Coin flips are independent from each other. One coin being flipped is not going to affect the other coin flip. So those are independent events. A dependent event is like what we did earlier today. When I took a coin, when I took a card, and the card was, let's say earlier we took out a card and it was a king, right? We took it out and we didn't put it back, and I was drawing my second card out of there, and I asked, what's the probability that this next card is going to be a queen? You notice that the probability changed. It was no longer 4 out of 52 because the 52nd card was in my hand as the king over here. So the probability that this next card right here was going to be a queen was now 4 out of 51. So that probability of you drawing a queen is normally 4 out of 52. It changed, right? It changed to 4 out of 51. Since it changes, that means that this card scenario is dependent. The probability does not stay the same given that the fact that something occurred. Whereas a coin flip, if you flip a coin once and you flip it again, probability is still 50-50. It does not change, right? So let's take a look here. Decide whether it is independent or dependent. And that's actually the first example we just talked about right now. Selecting a king from a deck, not replacing it, and then selecting a queen from the deck. That, like I said, is no longer going to be 4 out of 52. It changes, right? Because the king has been taken out and not replaced. It changes to 4 out of 51. I wouldn't even write that down. I'm just going to let you guys see that. Right? If you took a king out of the deck of cards and you don't put it back, it changes the probability of you drawing a queen now, and it actually is better now, a better chance of you drawing the queen. This is something that is dependent. Dependent. That is dependent. Right? If you draw a card out and you don't replace it, that is dependent. Look at number 2. Tossing a coin and then getting ahead, right? And event B is rolling a 6-sided die and getting a 6. And my question to you is this. If you toss a coin, does it affect your dice roll? And I know a lot of you guys are like, that's ridiculous, Donkey. Of course it doesn't. And I agree with you. That is ridiculous. It does not. You cannot flip a coin and have it affect your dice unless this is a computer game and you programmed it to do so. But in the real world, right, I can't flip this coin and have it affect my dice roll, right? It doesn't actually work that way. So you flipping a coin and you rolling a die, they are considered independent events. These are independent events, right? This one does not affect the other one. They are not related. The probabilities do not change along that one right there. Number 3 is a little bit subjective, but there's probably empirical probabilities that actually prove this to be true, dependent of each other. Driving over 85 miles per hour and then getting into a car accident. Does that look like it is dependent on each other? And you'll say, no, I've known people who got into a car accident who drove below 85% miles per hour. And some people are going to say, yes, if you're speeding, it actually can affect your driving. So which one would it be? What do you think? Independent or dependent? Speeding and having a car accident. What would you guys think? Dependent or independent?
Dependent. You can't get in a car crash without moving the car.
Oh, that's a very extreme example, but yes, you're right. That's one way of looking at it. Michael's going with dependent as well. Yeah, that is correct. This is a dependent event. These are dependent events, right? Driving over 85 and having a car accident, they are dependent. Okay. All right. I want you guys to try this one before we go for today. You're going to go ahead and I'm going to clear out your pair deck one more time. Let's go one more. And give me these 4 answers right. I'll put it as drawing. I'm going to go ahead and give you this clear canvas right now. Can you answer these 4 questions before you head out today? Tell me, is number 1 dependent or independent? Smoking a pack of cigarettes every day and developing emphysema, a chronic lung disease. Number 2, exercising frequently and having a 4.0 GPA. Are those dependent or independent? Did you hit through the... They could hit you though while the car is parked. Yeah, that is true. That is true. That is another possibility, Michael. That is true. Number 3, rolling a 6-sided die and then rolling the die a second time so that the sum of the 2 rolls even. Oh man, this one, that one I've had a good discussion with Mr. Rodriguez. I remember when I first saw that one. Is that dependent or independent? What do you think? And last but not least, a number ball between 1 and 52 is select from a bin, replaced, and then a second number ball is selected from the bin. Is that independent or dependent? And I'll get you guys to answer that out. And I'm going to give you guys, let's go with a minute and a half to do this one because it's a 50-50 chance. Tell me, what do you think it is? 1.5 minute timer. Let's go. Have you guys do that real quick. While you guys are doing that, I'm going to use this minute and a half to think about what do I want to get for lunch? What do you think is a good lunch today? I'm at school right now, so In-N-Out is across the street. That's a possibility. You know, a double-double is never bad. There's also the Poke place across the street. Panda. Panda's a little far. It's not across the street. They do have the Pho place across the street, the Vietnamese restaurant across the street. Earth. Do they still charge for parking at Earth? Because that made me very upset when they first opened. I was like, this place is not that fancy that you need to have valet parking or charge for parking. They did when they first opened, they charged for parking. Ooh, McDonald's. Costco isn't bad either. Costco pizza. But you know, there's always a line at Costco at 12. McDonald's is starting to sound good though. Get some chicken nuggets. Pizza in Costco is big. Yeah, it is. It is. I like it. Yeah, I love chicken nuggets, but I remember there used to be a commercial that was out. Chickens don't have nuggets, right? And I was like, that's true. Chicken don't have nuggets, but whatever is in chicken nuggets is delicious, and I don't care. My favorite was the I don't know if you guys are old enough to remember this, but the old chicken nuggets didn't used to be all white meat. It used to be like a blend of all the meats, and people were grossed out by the fact that it was like a pink paste. And I personally was like, this is amazing. It's delicious. And then they made it all healthy, which is still okay, but it's not as good as it, you know, what that old one was. El Tarasco is also there. No, it's no longer El Tarasco. They changed the name of it. I think it's changed ownership. I think it's changed ownership. Hawaiian food across the street. There's Hawaiian food here across the street. Wait, are you thinking, Christina? Are you thinking of the teriyaki place? Right, I think it's like Maui teriyaki, right? Is that? Oh, that Maui. That seems Hawaiian, knock me. Yeah, it's nasty. What's nasty, Mariah? The Hawaiian food or El Tarasco's? Because that's kind of important. Both. I thought Hawaiian food was okay. I like their macaroni salad. I normally don't like macaroni salad. I normally don't like it, but I like the one at Maui. Like you put some teriyaki sauce on there. It's delicious. Their mac salad is weak. It's all right. El Tarasco used to be good. Yeah. I haven't gone there since they changed owners, so I don't know if they're you're saying they're not as good. So well, we won't try that. All right, let's wrap this up. Smoking a pack of cigarettes a day, developing emphysema. I'm hoping you guys can see that is, I'm pretty sure that's dependent, right? One of these does affect the other, right? Getting emphysema is usually developed by smoking. So I'd say that's dependent. So hopefully you guys put that down in the pair deck. I will have this recorded, by the way. So you guys, yeah, good. I see 10 responses again out of 32. Wow, what can I do to get you guys more engaged on that? You tried Auntie Melly's though next to Elko? No, I have not. I haven't eaten around Elko since I went to Elko. That was back in like 2002. Man, I'm old. But anyways, I don't know. Wait, have I eaten around there? Wait, that's a lie. I have eaten around there, haven't I? I think there was something nearby that I've eaten. I just don't remember. I wasn't even born yet. Wait, is that right? Oh, that's right. This is 2021. You guys are seniors. You were probably born around 2002, 2003. Man, that's nuts. You should get Daphne's. Was born in 2002. Daphne's? Greek food, right? Yeah, we'll consider that. We'll consider that. Let's finish this up. Let's finish this up before I start thinking about food. I got to get going, though, to get food in 3 minutes. All right. Exercising frequently and having a 4.0 GPA. Some people could argue this to be dependent, right? But I'm going to go with independent because that's the general consensus on this one. But I've heard arguments that it is dependent because having a healthy body helps with a healthy mind. So you can see that works out. But I mean, I can't disagree with that, but I'm going to say independent anyways, right? They are independent of each other. Number 3. Nah, this one I've had intense discussions with. I say that it's independent, right? I say that it's independent. Mr. Rodriguez is arguing that it is dependent. So right now we're still torn on this. I say independent. Mr. Rodriguez says it is dependent. Which one's the right answer? We're going to have to use some actual calculations to prove which one is which. Now, the reason why I say it's independent is the first six-sided die is not going to affect the second six-sided die. Mr. Rodriguez is saying that what affects it is the fact that they need to sum up to equal to an even number. You need to add them up. So if the first one comes up odd, the second number needs to come up odd as well, so that it adds up to even. And if the first one comes up even, the second one needs to add up to come up even, so they add up to even as well. I'm saying they're independent because the probabilities don't change. I don't think when you roll that first die and roll that second die. I say that they're the same. He's saying they're dependent because it actually is dependent if the first one is odd or if the first one is even. That way they can add up to an even number. I'm going to let you guys figure that one out. What do you guys think? Do you think I'm right, or do you think Mr. Rodriguez is right? Now, I always say that I'm always right. That, most of the time is true. But Mr. Rodriguez is also the AP statistics teacher. He teaches the AP level of this. So I'll let you guys think about that. All right, last one over here. I'm going to just give you this answer. This last one is going to be independent because you do replace the number. That's independent. And I'm going to pause it there. We're not going to actually get to the homeworks of this because we did not finish the notes. Do not submit the notes here. We have not finished this up, but please make sure that they are saved. There should be a little save icon. Make sure you click on that before you go today. And that's going to be it for me today, guys. Please remember, there's no school on Monday, so I will not see you guys until Tuesday. And that's going to be it. We're going to do a simple warm-up like we did today on Tuesday instead of a quiz, and we'll do it on Pear Deck, and I'll give you some points for that for participation, and then we'll start doing quizzes after that once we finish this up. All right, guys? So other than that, have a good weekend. Stay out of trouble, stay out of jail, and please don't get pregnant. I'll see you guys on Tuesday next week. Have a great weekend, guys. So long. Farewell.